Um, I I'm Josh, and I work with Industrial Compressor Solutions, and I am doing this webinar with compressed air towards zero, and we're going to be looking at the efficiency of demand side optimizations. The webinar is called "Where Are My Savings?" Please, in the beginning, let me tell you that this concept is too big for one webinar. And as always, the purpose of this webinar is to hopefully make us think. It's not necessarily to prove a concept right or wrong. It's just that maybe we can evaluate it, evaluate ourselves, evaluate our own level of knowledge, and then go out in the field and see if we can repeat some of the things that we're talking about this morning. So, a quick story. Once upon a time, there was a facility with two 18 kilowatt compressors. They had a high percentage of leaks, and they were very interested in trying to reduce the amount of leaks and save money on their power bill. So we went out there and did a leak study, and we found that 71% of the overall demand was leaks. So how much is it worth for that customer to fix those leaks? So again, my name is Josh. I've been in the compressed air industry for about 25 years. Most of my career has been in the demand side of the system. I am a general contractor and a mechanical contractor. But yeah, so I spend most of my time on the demand side and doing demand side auditing and optimization. Very proud to be a member of Compressed Air Towards Zero. I am part of KGI in rotary positive standards as well as system assessment. I represent the United States and ANSI for safety in compressed air. I am a member of the AICD as well as the Palmetto chapter of the Project Management Institute. So again, where are my savings? First things first, we kind of need to talk about and make sure that we're all on the same page as to what savings are and or means. So at the risk of proving to all of you that I am not an accountant and will never be an accountant, when we talk about savings in a facility, we talk about a couple different terms that get thrown around. The first thing I'd like to point out is the difference between cost savings and cost avoidance. If we have an electric bill that we are currently paying and want to reduce that, that is an example of reducing existing cost and cost savings. Whereas cost avoidance is an effort that we do to prevent having to pay something. That might be an example of that might be that we pay an extended warranty on our service so that if we lose an air end or a motor, the service company will pay for that instead of having to come out of our pockets. Now, when it comes to total cost of ownership, that includes everything from start to finish that we have to pay for a piece of equipment or for a system. If we make improvements or change our operating mentality without spending, then we can affect the total cost of ownership through cost savings and cost avoidance. But if we have an expense related to that, now we might hear a term like return on investment, where we're trying to evaluate how long it'll be before that savings is realized. So my contention and what I want to talk about to you guys today is that this is not exactly right. In my experience, there is an efficiency to our optimization methods. And if we are going to present to the customer some method of optimization, it's in our best interest as well as the customer's best interest to evaluate the efficiency and expectations of what that optimization is going to bring, and how long it's going to last. So here's my super slide for the day. Um, this is a very, very basic illustration of the fact that the compressed air system cost goes up over time. If we perform an optimization, we are attempting to reduce that cost. But I'm going to show you today that there's inefficiencies in our optimization. Not only am I going to show you that there are inefficiencies, but I'm also going to talk about the fact that our optimization decays. So what ends up happening is, even though we made an improvement or optimization, we sometimes are not able to maintain the system at that optimized position. So now that efficiency, that optimization decays back to the original line. This is very similar to holding a balloon underwater. A lot of times, like we look at the people on the supply side of the system, and they're selling these really beautiful, high speed, super efficient air compressors, and every one is more beautiful than the one before it. Whereas on the demand side of the system, a lot of times it's like we're telling our customer that their baby's ugly. And when we talk about demand side optimizations, we are forcing that system to a place that it does not naturally want to be. So I do try to use that analogy of demand side optimization is very much like holding a balloon underwater. It doesn't always take a whole lot to get that balloon underwater, but it does require that we consistently hold it there, and we force it to stay there. So in that regard, as if we set benchmarks and thresholds to an optimization, then as soon as it exceeds that threshold, then we institute another optimization to keep the system operating where it's supposed to. And here's some of the things that affect it. So if you are making an optimization in your facility, but the compressor room is less efficient at the new demand profile, then your efficiency will be reduced or your savings will be reduced. If you are running two compressors in cascading pressure band and you are running into the second compressor, then your pressure is lower. Your pressure is in the lower of those two compressors. If you make an optimization that turns off that compressor, you do have a power reduction there, but your entire system is going to operate at the higher pressure of the first compressor in that cascading band. So you do have a percent of the savings that you would have had lost to operating at a higher pressure, depending on your pressure control in all four positions of the facility. So that's at the compressors, that's at the plant level, that's at the zone level, and then at the process level. When you do pressure reductions, you also reduce usable storage and receiver tanks. So intermittent demand in the plant is now having to be accounted for directly from the compressors instead of through usable storage. If your part load efficiency isn't good, and or your unloaded power is high, when you change the cycle rate of the compressor, if your compressor is not efficient at varying demand profiles, it's not only is it going to not give you the power savings you were hoping for, but it's also going to cause additional wear and tear on the compressor. If you make an optimization, but you don't but you don't remove the old piping and system, now you have the potential for leaks and future leaks, but you also have the potential of somebody else tying back into it at a future date. If we're looking at putting using storage across a receiver or process receiver to handle intermittent demand, and we have to increase the pressure of the system to do that, then the savings that we see on that individual process are mitigated by the overall increase in pressure and the cost to provide that system at a higher pressure. And then we also have the cost of the change of technology. If we are, for example, let's say we use a pneumatic amplifier. A pneumatic amplifier will increase the pressure to a specific process or intermittent demand, but at the same time, it uses compressed air to further compress the air that's being supplied to the process. So there's an inefficiency. There's an inefficiency directly in that. Now, when we talk about decay, we talk about a couple different things that cause our optimizations to decay. The first one is if it's adjusted back. It could be as simple as a valve lineup. Depending on the different mentalities for optimization, some people will remove the system's capabilities to operate in the old way. And then some people will use valves and or piping to make it where you could still operate in the other way and basically bypass the optimization. But in doing that, there's risk on both sides of those, right? If you take out the old way of doing things and you made a mistake or didn't account for something, then you no longer can operate in the way that the system was operating. That has some risk to it. On the opposite side, if we leave the way of if we leave the first way, the unoptimized way of delivering compressed air, then we have the potential that somebody would change a valve lineup and bypass what it was that we are trying to optimize. So the next one is more so in the leak load, where if you optimize something that's not a permanent optimization, like leaks, if you fix leaks but you can't keep them fixed and you can't prevent new leaks from coming, then you end up having a leak load. Now, the leak load ebbs and flows with the system and as a function of time. So yes, it's important to make those optimizations, but it's also important to understand what the decay is of, or the increase of the leak load, so the decay of the optimization. Employee changes. We might have a plant manager or contact at a facility that is bought in and on board to make optimizations. But as soon as that person is no longer in that chair, it is then up to us to have conversations with that new person, because otherwise they might come in and just change things because they don't see why we're doing it that way, or they have different ideas on how it should be done. The system can be modified. Modifications to the system, especially if we don't understand the interrelationship of optimizations, other processes and other things tied into the system can affect the optimization, whether it be pressure reduction or process storage, whatever it is. And then if the plant needs change, if the manufacturing needs change in a facility, that can completely upend the volume and pressure of air that we are delivering to different sections of the facility. Okay, so we're going to look at 5 different types of demand side optimizations. The first one is leak and leak load reduction. The second one is pressure reduction and pressure control. The third one is going to be adding storage. The fourth one compressed air to other methods, and then the fifth one is piping optimization. I feel like I'm speaking in a racing voice. So if somebody could maybe Menno, Patrick, if somebody, Mr. Kieran, if somebody could comment down below if I am racing as fast as I think I can. It is please excuse me. It's early morning here, and I am definitely running off of espresso right now. All right. So first, leaks and leak load reduction. Thanks, Daniel. So when we talk about leak load and leak reduction, I first want to put up the control comparison between power and flow. So in the story that we talked about in the beginning, we said that the customer had two 18 kilowatt compressors. These two compressors were running in cascading control. So it was local controls. Both compressors are oil flooded rotary screw, and they loaded and unloaded, and the load set points were offset from each other so that if the demand profile exceeded what one compressor could do, pressure would drop to the point that the second compressor would load, and it would continue running without operator action. So in this case, and I apologize for not changing these to unit or worldly units, but we can say 236 divided by 35.315 equals, so that was right by 6.7 cubes overall, and around 3 cubes reliable without having the second compressor coming on. But efficient operation was really in the top 10% of that compressor. Now, when we got there, we noticed that the second compressor was turned off just temporarily, and the first compressor was running right at the top of its band. Now, the interesting thing is that it was running so much in the top of its band that what ended up happening was the compressor was staying fully loaded, but system pressure was moving up and down while running at full load. So we're going to talk about that a little bit later, but this is another example of instead of varying flow to maintain a constant pressure, we were varying pressure at a constant supplied flow. As we said, the leak load was 65% of the overall demand profile, and that was right at 2 cubes. But if full power annualized, which it was $12,684 US, 65% leak reduction does not equate to 65% power reduction. In fact, of the savings that the customer thought that they were going to get, they weren't going to see $8,244 a year in savings. They were only going to see $2,900, based on the fact that we don't go proportionally down to zero. We didn't have linear efficiency across that demand profile. So we have to follow the curve of the compressor. And what we end up seeing is our change in power cost is only $2,900. Now, if we had promised the customer $9,000 or $8,500, then we would have been setting up that customer for failure. But I got to ask you, is even that $2,900 real? We have to understand, or we have to take into account the decay of the savings. Now, and I'm not saying that if you have a leak in a fitting and you fix that leak, that leak will necessarily start again. I'm not saying that. But what I'm hoping you'll consider is that the leak load is in itself a number. It changes by pressure fed to the leaks, and the leaks get worse over time. So even when we make a repair, at the same time, immediately more leaks are happening. So we can bring down our leak load, but it is slowly going to come back up, and then we will have to commit to another action. But the amount of time that it takes to deplete that savings is important for calculating how much the customer would actually save. I know this is a little bit small, but we already said that the reduction in power was approximately $2,900 back to the customer if they were successful fixing 100% of those leaks. Now, if we could, I will oversimplify it for a second and say that although this is not true, we are going to assume that there is a linear decay in the optimization. So what I'm saying is that when we fix the leaks, in this case specifically, I'm going to show a model where the leaks are getting worse in a linear fashion, which isn't necessarily true. So it is a little bit oversimplified for the purpose of training. So if 2,900 is my expected savings per year based on being able to reduce 100% of that leak load, those leaks would have to either stay completely gone. The leak load would have to stay zero for 12 months to get that $2,900, or in a linear form, it would have to return back to its original position in 2 years. After 2 years, you would have had the savings promised, the annual savings promised based on linear decay. But how about that second compressor? In a position where you have two compressors, load unload, oil flooded rotary screw, at that 3 cube point, or almost exactly 3 cubes, at that 3 cube point, you can be in a position where compressor one is running fully loaded and the second compressor is off, or you could be at that same flow rate. You could also be in a position where compressor one is running fully loaded and compressor two is running unloaded. The difference between those two positions is zero for flow, but in this case was $6,300 in power cost. Just by not allowing that compressor to run in an unloaded state, we have a cost avoidance of $6,300, as well as the fact that in a system where we have two compressors, the moment we're running that second compressor, now our reliability position has changed. And the moment we're running that second compressor and we're required to run that second compressor, we don't have a backup compressor. One compressor shuts down, hiccups, trips out, whatever, and now we can't maintain plant pressure and we're down. So now we have a $2,900 savings, or some percentage of that we can try to get, a percentage of that we can fix, and a percentage of that we can keep, as well as $6,300 in this position of not having to have the second compressor on. Going back to the financial terms in the beginning, this is the difference between cost avoidance and cost savings. Now, both of these have efficiency attached to them. So in this example, there's a couple different costs that we have to look at with the customer. And I think one of the critical points is having the customer understand that we're not over promising anything. We want to be very realistic with the customer as far as what are they intending to save, what is the cost to do the leak study and the cost to make the repairs, what is the time to deplete the savings, and when are we going to trigger another leak study. um, this conversation ended up being really positive with the customer because we ended up finding out that preventing the second compressor from coming on is the most important thing. And that was good enough to change the employee's mindset on fixing leaks in the facility. And they had their maintenance people charged with going through after hours and fixing leaks. So their intention is to keep that leak load under the point where that second compressor comes on and reduce costs in the leak repair and the leak auditing by taking more of it on internally. Now I make halfway of a little joke here. Um, it's a little joke, but I also want to be careful that I'm not being disrespectful to people that sell air compressors for a living. When when a customer says we don't have enough air, it is natural for a compressor salesperson to evaluate how much air is being used and provide an air compressor to solve that need. They might not be trained in the demand side. The customer might not even be wanting them to look in the demand side. And in that scenario, the compressor salesperson is doing what they are paid to do by putting in, hopefully, the most efficient and most reliable offering possible to meet the customer's demand, instead of where here we're talking about trying to optimize that demand before making purchase. So this goes to what we're saying about when that demand profile increases, and when the demand profile increases, if we don't have a backup compressor and we don't have monitoring, automation, controls, what ends up happening is this demand profile keeps increasing to the point where the compressors can't, the supply cannot overcome the demand requirements. In that case, pressure starts dropping until the point that something starts failing and we'll get a call. But in that case, the plant's already down. So my argument is use benchmarks and thresholds to say, hey, let's keep the demand profile short of what is needed for the backup compressor to come on, and let's sound the alarm. Let's sound the alarm when we go into our backup compressor. Now, what ends up happening in that case, if we do that, then my question and my challenge to you all is, how do we know how close to that threshold line? And I think Mr. John just asked a question about what is the minimum permissible leak. Well, if we're saying that our critical point in this case, our critical point is that we do not want that second compressor to come on, then isn't it advantageous for us to know how close we are at any given time to reaching that point? Doesn't that help us make decisions? If we know that in this case we have 3 cubes before the second compressor comes on, if we're operating at 2.9 cubes 10 hours a day, then we are right there at the point where we are about to change our reliability position. And in that case, now we have to answer with a rental compressor, with an additional compressor, or with a demand side optimization to get us back to where we can operate properly. So as far as leak and leak load reduction goes, a common practice is reducing the flow being proportional to a reduction in power. That's just not correct. As the inefficiencies go, the effect on pressure, especially with unregulated processes, If we have to shut down to repair, leaks, there's a cost of having the line down or the process down that has to be accounted of against it. Compressor room efficiency at the new demand profile, running leaks versus shutdown leaks, depending on where and when we measure the leaks. If we look at a process and we supply air to that process, but the process is off or not in running condition, any leaks that are on the secondary side of the solenoid valves internal to the process are not being fed. So you lose the demand, but you also lose the waste. So depending on when and how you calculate your leak load and when you're doing your leak studies and how you're doing your leak studies, that's going to tell how much you're going to capture as well. Now, if your leaks are on the downstream, the secondary side of the solenoid valves, the cycle rate of that process equipment is also going to affect that savings back to power. So if that line is only open 30% of the time, we can't account for 100% of power savings, even on a perfectly in a matched efficiency from initial demand profile to new demand profile. Even if the compressor room has the same efficiency across that range, you still have to take into account the cycle of any leak passed on the downstream side of the solenoid valves. Inefficiencies as a function of time. The leak load is constantly increasing, and 2 years at the same leak load with a linear decay, or 1 year with no change in leak load, to be able to maintain the annual savings of linear reduction. Okay. All right. So pressure reduction and pressure control. Yeah, I thought I hit it again. Pause for effect. So when we look at pressure reduction and pressure control, we end up taking into account the overall system. And I am actually going to switch slides real quick. So I'm going to jump around. So pressure reduction is taken in 4 separate places. The first place that we control pressure is at the compressors. We can do this in local control, or we can do it with automation for the compressor station overall. The second place that we can control pressure is on the plant level. That is going to the entirety of our facility. From there, we can also control pressure on the zone level. If we have critical processes or a process group, we can control pressure to that entire area or zone. And then the fourth is the individual processes. But when we talk about efficiencies and demand side optimization, having an understanding of the pressure mapping as well as the flow mapping is going to determine where, when, and how to do these things. Now, there is benefits. There's benefits to controlling pressure in multiple different places. Sometimes there's benefits to just control it at the plant level. So, for example, if we needed a 6 bar pressure to every single process and process group, then we might want to control that at the plant level. Now, what happens though is if the piping is undersized or marginally sized, we might choose to leave it at the higher pressure and regulate it down at the zone level or process level instead. We also have the backup aspects of sometimes we want to regulate pressure at the processes and then additionally somewhere else behind it. That might be a stepped approach, or it might be even. Remembering as well that there's other pitfalls to pressure control. If the pressure control device is not properly sized to the process flow requirement, then it'll either hunt or droop. So, for example, if you have a flow controller and it is rated for call it 100 cube, you're going to be at about 30 to 40% of that. It's going to be too small for it to be able to control that pressure. And you will see that the secondary pressure will start going up and down. It'll hunt. It'll hunt because the control method is just too large to be able to handle the constant pressure control. If we exceed that 100 cubes, then we end up seeing droop. It just can't maintain the pressure as well. So the relationship, though, of these different pressures is going to tell us what to do, but it's also going to impact what our potential savings are. If the zones are all at 7 bar and the plant is also set at 7 bar or 7.2 bar or 7.3 bar, then you have the inefficiencies of the piping and the fact that you move that the fulcrum point of the system. And by fulcrum point, as a side note, I mean the place where compressed air is no longer coming into the system, it is now going out of the system. So if that is designed to be in the receiver tank at the suction side to the plant, so at the discharge of the compressor station, then all air going into that tank is from the compressors, and then the demand side and distribution is taken from that tank. If we remove pressure control at the plant level and have properly sized piping on the distribution network, then our fulcrum point then moves over closer to where the process points are, because now we are taking air. We are on purpose. We are taking air from different points in the distribution network to supply each other. So the compressor room is not only the compressor room is supplying air to the processes, but now the rest of the system is also doing that. So we do want to be on purpose when it comes to the fulcrum point, but we want to understand pressure and volume mapping around the plant to know how they affect each other and what our intentions are for savings in relationship to those things. So in this example, I'm going to switch to European. At 11 a.m., I have to give this webinar. We believe that it will be more in the United States. So I went ahead and put multiple pages in here. So in this facility, we had 5 different types of processes. They operated off at different pressures and different volumes. But when we first got to that facility, plant pressure was dropping to the point that they were losing product, and they had a really high scrap rate. So when we did our process we did our process mapping, our pressure and flow mapping, we were able to gain a little bit of picture of what the demand profile was, and we decided that pressure control was one of the key things that we needed. So in the beginning, we had 10 bar on 2 of the processes, 7 bar on a third process, and then the last 2 were stated as also being at 6 bar. But we found that those were not actually correct. And when we talked to the customer, we put in some pressure control devices and got the pressure down on 2 of those different styles. What ended up happening is that the customer went from spending $192,000 a year in power to $55,000 a year. When we talk about inefficiencies, though, in reducing pressure, we have a scenario here that we found a couple weeks ago where repeatedly we are having situations where the demand profile was changing, but the power on the power from the compressor room was not changing with it. In this case, between position 1 and 2, there's almost exactly 10 cubes of difference in the demand profile with only 3 kilowatts of change at the compressor room. Now, if you consider that for a second, if you reduced the demand profile by 10 cubes, if we reduce the demand profile by 10 cubes and don't save any power whatsoever, that there's a little bit of liability to all of us, right? So again, we want to be careful with our pressure mapping and our flow mapping to get a true understanding of what's going to happen and where. I would like to point out back to this slide that if we have good pressure control at all 4 places, but we lose it to any one of them, then we immediately change the nature of the entire system. In this system right here, as well as the system we were talking about with the 3 cube operation, when that second compressor was off, we found that the first compressor was running fully loaded and the pressure was changing while the load was constant. And the system moves back and forth. Both of those two systems actually were having similar attributes. When operating properly, when the demand profile is less than the supply, the capability of the compressor station, then load changes on the compressors to maintain a constant pressure or constant pressure band. But once the demand profile exceeds the supply capabilities, the first thing that happens is storage is reduced in any receivers that you have. And then once that is depleted and pressure is constant across the line, now if the demand profile is still higher than what the supply can provide, then pressure is changing while the the supply side is constant and fully loaded. Now, I'll point out on these, in the first case, supply efficiency is highly dependent on part load efficiency, and reliability position varies depending on what equipment you have in the space and the relationship between the supply and that overall equipment. On the other case, where the demand side is higher than the supply capabilities, now as the demand increases, pressure drops with all compressors fully loaded, and you actually see an increase in efficiency as the compressors see it. So they are running at reduced pressure, fully loaded. So effectively, it might be a little of an oversimplification, but we're saying we're reducing artificial demand out of necessity. So if the compressors are running at 6 bar instead of 7 bar, but still fully loaded, they're now running at a lower pressure. They're running more efficiently, and therefore your specific power is better. Albeit you might be increasing your scrap rate and scheduling production, but according to the compressors, they're loving it. So when it comes to pressure reduction and pressure control, common practice, automation, reducing pressure drop, installing pressure control devices. We talk about inefficiencies. We talk about compressor room inefficiency at the new demand profile, reduce storage for intermittent demand, and then also off-shift demand reductions or off-shift demand requirements might further put that compressor room out of spec. Inefficiencies is a function of time, whether these pressure reductions are turned off, whether pressure is turned up, uh, whether they made changes to the valve lineup. They made changes to the valve lineup for maintenance or for repair, but then didn't return it back to the position it was supposed to be in. And or if you have pressure devices that are broken. We're probably going to have to speed things up. It's already 5:46, so I'm going to push through a little bit faster. Um, so I say. So the next one is adding storage. We have some common usage for receiver tanks in a facility. In the compressor room, it can be for pressure balancing, it can be for water removal. Um, on the plant level, we have dry storage between the compressor station and the facility, or in the distribution. We can use receiver tanks at the end of a long piping run to minimize pressure drop. That's a Band-Aid solution, but it does work. And then as relates to processes and process groups, you have process protection as well as event storage. And in the process protection, you're talking about pressure reduction as either a function of the cycle of that individual process, or you're talking about changes in utilization upstream on that line. So other processes in the same line robbing that air. And then event storage is relatively self-explanatory. So in the first one, we install a receiver tank, but if the demand is above the system capabilities and we have a wet receiver, we can overflow the dryer. And now we're having air quality issues. If we have a receiver tank before the dryers and we have a bad drain trap and that tank fills with water, now we lose the pressure balancing and the receiver is effectively not there. And we can send water missiles into our dryers, which is not fun. On the intermediate storage, if we have a loss of pressure control, the storage is gone. We were just recently in a plant with 450 kilowatts of compressor, but they lost all of their pressure control. They have a 10,000 gallon. I'm not going to try to do that math here as we're already running late, but they had a 10,000 gallon receiver tank and they were wondering why it's worthless. Well, it's worthless because there's no differential pressure across it. Distribution. If the demand profile increases, the receiver will lose effectiveness, especially depending on how tight you size that receiver for the pressure drop that you saw when it first started happening. But changes to that demand profile are going to change the effectiveness to that receiver tank. On the process protection, if the check valve fails, it'll just rob the system. It'll rob the storage completely. And then on the event storage, if the demand profile changes and the supply pressure to that receiver tank is reduced, then the differential pressure across that receiver is also reduced, and thereby the usable storage is reduced. So we talk about adding storage, installing a tank, check valve, pressure control. But on the inefficiencies, if there's a constant demand, the receiver tank's not going to do anything. The wrong size and or pressure feed line can create issues, especially when you're using it for intermittent demand, where you evacuate the contents of that tank. But if you're not metering the air back into the tank, then you can cause the same problems that you were trying to avoid. Changes in cycle and or broken components can affect storage capabilities very, very quick. I met a gentleman earlier this year named John Bilski, and he's a wizard when it comes to drain traps and such in a compressed air system. And it makes me giggle sometimes, because how many times have we seen where one bad drain trap or one clogged Y strainer allows a receiver tank to fill up with water, and you are sitting there staring at this huge receiver tank, but when you're watching how the system operates, there's no receiver, right? So another thing to be aware of. So compressed air to other method. And it's what do you call it? 1151. I got to be careful. Compressed air to other method. When we remove compressed air processes from the system, and or isolate piping and processes that are non-critical or not needed at the time, we have to go back to the inefficiencies of the compressor room, or the minimum operating capabilities of the compressor room. I was recently at a facility, and they are using 990 kilowatts of compressor, or is what they have on the system. They have 335 kilowatt. So what is that? 1,005 kilowatts, right? They have 335 kilowatt compressors, but they're currently running 7.5 kilowatts of demand. It's absolutely ridiculous. So what ends up happening is, I guess, I don't know if I have a pointer. I don't know if the pointer shows on the screen, but if we chase the red line and look between 1,400 and 1,500, it looks like there's a chair. Now, the funky thing about that chair is that the back of that chair is the only point where the compressor was required to load. After that, the compressor just sat in the unload position before shutting off. But in this case, we saw between 11:15-ish and 2:15, the compressor didn't have to load. The demand profile was so far underneath the capabilities of the compressors. And this is a little bit of an extreme example, but what is the effect? What is the effect? This is one of my challenges to you guys, is what is the effect of the optimization? What is the efficiency of the optimization, the decay of the optimization? What are the things that are not what are the things that are not positive? What are you going to have to overcome under the new operating conditions? There's no magic solutions. We say this a lot, but there are just no magic solutions. We are going to have a set of challenges that we're going to have to account for no matter what. And in 2 minutes, I'm going to wrap up by hook or by crook. So piping optimization along the same lines, that same plant that I showed you a little bit earlier, 5 different styles of drops. The flow rate comparisons were made. We ended up figuring out that the cycles were not the same. So we're able to store air for intermittent demands, as well as turn off air and cycle things differently. And that also contributed to getting that system operating at a lot less cost. Now, sadly, though, it's important to say that the customer did turn off this system. Not only did they turn it off, but instead of running 4 compressors like they were before they called us, they bought 2 more. So now the customer's running 6 compressors. They decided against holding that balloon underwater. They decided against maintaining that level of optimization. They'd rather pay for additional equipment and just take compressed air off their plate. That was the effects of a change of leadership, and it just threw us out of the way. So running additional pipe, installing big pipe, inefficiencies, compressor room at the new demand profile, old piping and leaks, higher pressure versus unregulated processes, unaccounted for costs, The decay is going to be changes to the demand profile, loss of pressure control, and change in personnel. So again, there is an efficiency to what we optimize, and there is also a decay associated with it. We need to be on purpose when we figure out how are we going to maintain the optimization that we're trying to provide for our customers. There's plenty of reasons why the savings aren't what we thought they were. There's plenty of reasons that the gain is not maintained. We can regularly walk the system. We can permanently monitor the system and be noticed to change. We can do training. We can label valves and valve lineups, including pictures, create action and contingency plans, partner with our customers, and have a team approach to managing the compressed air system and optimizations. Strongly suggest not over-promising. And there is just no magic solution. Now, Mr. Wojcik, I don't know how to do questions on this, but are there any questions?
So far, we don't see the questions. In the meantime, perhaps it will come. I have to admit to say that it's not that easy. The leaks are not that easy. So if you do not perform the holistic approach, you may think that you're solving problems, but you are not solving those in real. So if any questions would appear, our director behind will display it. Okay. There is a question. Kasia will show it to us. Okay. Here you are, Josh.
I'm so sorry, I don't understand one of the words. Are you helling? I don't know the word helling, H-E-L-I-N-G.
All right.
Melanath, would you please clarify what you mean by helling, H-E-L-I-N-G?
All right, we have to wait. It's helping to measure the efficiency of compressors. Probably that's the question.
Helping. Okay, helping. Measuring the efficiency of compressors is critical to me. Thank you so much for your clarification. Measuring the efficiency of the compressors is really important to me. One of the things I like to do, I left it out of this because it's more on the supply side, is I like to measure flow at a couple different places in the system and then revert that back to the power. So I'm measuring specific power at multiple places in the same system and doing comparative analyses of that specific power. So the efficiencies of the compressor, sure, but by looking at the variations through the system, it reverts back and shows us changes in efficiency in the dryers and filters, but it also can show changes in the effectiveness of usable storage and what you're delivering to the facility. So yes, I do measure the efficiency of compressors on a permanent basis, and I hope that answers your question, sir, or Malna.
Okay, I can see that some questions is coming as well. So let's wait for a while. Okay. Thank you very much. Okay, don't be shy. Ask the questions. As you see, the expert is in front of you. Okay. All right. We have good response that the answers came the way where are my questions. That's really good, because it's usually expectation from the end user that since we approach the plant, we will bring the savings overnight. But it's so complex and there are so many components. So, all right, there is a question. When you tell measuring at different points of the system, how can it be measured?
All right. So on the demand side of the system, if you are using flow and pressure in one direction, so it does depend on the overall mapping of the system. So we could take pressure as a function of where it is supplied to the distribution network. So if we said, hey, it's 7.0 bar at the point that the compressed air enters the distribution network, then we can look at pressure drops throughout that system and see how they vary to each other. So if the system is being supplied by the compressor room, then you shouldn't see where an increase in flow on one process is being robbed by the other processes. Instead, it's being managed from the compressor station. But by looking at flow and pressure and mapping that in your facility, that is how it's done. But it is done with flow meters and pressure transducers. I know there's some people that do it with velocity meters, but I have not personally done it that way. So while I mention it, I'm not the guy to talk about that. Several pressure reducers in a series. Patrick, I love that question. So this goes into that pressure and flow mapping as well, right? So depending on the relationship of the pressures, so we were in a plant a couple of weeks ago where the maximum pressure they need in the overall plant is, I got to do the math to switch it to bar, 7. So the maximum pressure that the plant needed was 7 bar. There was 1/4 of the facility only needed 2.3 bar. Well, in that case, it makes sense to have the two separate pressure controls, right? And then the secondary question is, what happens if that one pressure control device at the individual zone failed? If it's set at 2.3 bar and that one pressure device changes, we just went from operating at 40 kilowatt to 90 kilowatt, depending on the pressure in the rest of the system. So we had a high risk. We have a high risk. Now, we don't want to oversize our pressure control devices, but we don't want to have a lot of loss in them either. So there's an argument of, do you have a secondary pressure control at the zone level, or do you put that at the process level and back it up that way? Now, in one of the other facilities, two of the other zones, the 75 PSI was the same as the plant level. So to have the backup there, then the question was, do we want the backup on the zone level, or do we want to have the backup on the process level? Those decisions, man, I saw one a couple weeks ago where I wanted to put it on the process level, but the process level was so corrosive, we ended up suggesting to the customer to run a stainless steel subloop and control pressure outside of that caustic environment to those processes there. So there's a lot of factors that go into the 4 different places that we do pressure control. There are questions of, what are you going to lose in pressure drop if you try to back it up against the impact of failure or the cost avoidance model? So I would say that there's it's a relatively thorough discussion, and a team approach is what's going to put you in the right direction and solution, in my experience.
Okay, we have another question. Okay, here we have it. Oh, even more. Okay. Okay.
Oh God, this is a great question. All right, so man, these are awesome. Man, for 6 o'clock in the morning, I'm halfway motivated. I might have to go run. All right, so pneumatic components are designed to run at a pressure, but a lot of times that is a max pressure. That's not the minimum pressure they're needed. Heck, I can't even tell you how many times I've seen a system that is designed for 6 bar or 6.2 bar, and then just to find that there's 4 kilometers of 4 millimeter tubing and a 1 bar cylinder at the end of the line. Like, when we talk about the potential to make savings and optimizations on the demand side, I would almost argue that if we don't go into the processes, the majority of the savings is going to be in optimization of the supply side in the compressor stations. But my goodness, if we are willing to go past the regulators and into the processes and work with the machine builders and the process guys to optimize the processes and the process pressure, the majority of the savings become on the demand side.
Yes, and one thing to add, it's certainly the tendency to reduce the pressure in general. Very often we see in plants which are owned by Japanese owners, they keep the pressure at 4 bar or below. The tendency to keep the pressure at 4 bar, it becomes kind of idea. So, okay, we have one more question. Okay.
Yes. Yes, there's definitely benchmarking is different per application, and there's also different strategies for doing it. Sometimes we take a known acceptable pressure and then a questionable pressure. So if, let's say that we're running at 7 bar, but we all agree that we can run less than 6 bar, well, then relatively fast, maybe even over a couple of weeks, we can take down the pressure to 6 bar. But once we start approaching 6 bar, we're no longer all in agreement on how to reduce it further and or what the effects are. So really, once we get past for the known acceptable pressure, once we start approaching that, we really have to be careful. We have to be incremental, and we have to stop and check every single adjustment that we make. We have to circle back around and see what is being affected by it. We also are going to have a threshold to optimization for increase of risk and perceived increase in risk. If we're causing so much anxiety to the plant operators and plant management, they're going to be like, nope, just buy 2 more compressors. I'm already getting screamed at for an hour before I come to work, and 3 hours after I get home, I'm not doing it at work. More compressors. So, but when we look at it by process type or industry type, there is still the comfort and I guess that threshold to change for that plant operators. It doesn't matter if we've done 35 different automotive plants. If we go into the 36th automotive plant and the plant manager isn't down to reduce pressure, we can't just go out there and be like, well, everybody else does it like this. That's not. You'll get 2 orders. Get out and don't ever come back.
I was doing that 20 years and you're coming to change it. Why?
Yeah. So yes, but to answer the question, there are different benchmarks and maybe like ideas of where you can be based on different types of applications, but you're still really going to need the buy-in from the customer and do it at their threshold for change, right? And threshold for optimization.
All right. Next one.
Great. Oh my God, these questions are awesome. So electric solutions better than pneumatic? It's a different set of challenges. I've seen scenarios where they try to use electric. Hey, I've got a at-home example. Even though I love compressed air more than anything, I also love Milwaukee tools. And I bought a battery operated nail gun. And I was very motivated because I have a 6 meter by 9 meter deck that my wife asked me to put a new top on this summer. So I did. What I found out though is I can't have my cute little carousel battery pack sitting out in the sun, because when I switched to electric, all the batteries were dead in about 4 seconds, and I ended up having to go get the air compressor and run the hose out and get the pneumatic gun, right? It's not as cut and dry as just saying like, hey, like, do you have power out somewhere? I can answer that same question in regards to drain traps. Sometimes I like to have a powered drain trap. I like to have a dry contact to know when it's failing. But if there's no power out there, what is the cost to run power out there? Is it a safe environment? There are environments where compressed air is the best way to go, and there are also issues where electric is a lot more efficient. And I'd like to stipulate, John, that part of my answer is based on the regulation of the electrical system per the NEC or whatever codes, whether it be ISO or whoever, right? Like you have safeties starting at 15% over full load, and those are adjusted based on overloads, breakers, fuses. All of these things are ensuring that the electricity is kept to where it's supposed to be. If that power requirement changes, it will trip out some aspect of that system. In the compressed air world, we just buy more compressors. We don't fix the piping. We don't add piping. There's just more compressors. So maybe there's a great case for it while it's in its design criteria. But once it starts failing or adjusting out of that, the electrical is a lot more likely to catch that increase in power. So that is a great question, and the answer is all over the board.
Okay, it seems some other question is coming. No. Okay, one more.
So yes, management, automation in the compressor room is specifically designed to efficiently react to the demand profile. Now, the automation in the compressor room is not optimizing the demand side. It is doing its level best with the equipment that it has in the space to utilize those pieces of equipment efficiently as possible and reliably as possible to supply that demand profile. It does help. It can help compressors run at optimized points. I got to tell you, when you talk about changing in plant personnel, man, Wojciech, I would die to know how many people you've seen over the years where like that one plant contact moves or gets promoted, and the next thing you know, the automation is turned off because like nobody knows how it was supposed to run. It's turned off for maintenance. Nobody knows how it's turned to run. I think whether you talk about compressor management systems by the OEMs and or the ones that are separate, neutral, brand neutral, they both have different levels of capabilities. It's highly dependent on the people that are operating as well as the people managing it, to see what the efficiency is of that optimization, because there's also an efficiency of the supply side optimizations as well, and that varies over time and by all the people involved. So
yes, thank you. All right. Yes, we will be very, very pleased to answer more of your questions. Next webinar will be published with the date information in January. So if so many questions, we might come back to this and say more about this. So, Mr. Wamser, thank you very much for your presentation. I'm impressed and would like to continue. I will try to ask you more out offline. So I hope we will see next webinar, and of course our conference. It's 1st of April 2025 in Hanover, during Hanover Messe. So thank you very much, and Merry Christmas.